This is Rubber Expansion Joints, Basic Applications to Advanced Solutions, a two-part webinar. The first part focused on system design and optimization. This part today will focus more on system reliability and efficiency. I would like to thank again the Hydraulic Institute for giving me this opportunity to validate the importance of rubber expansion joints in pump piping systems. I have said that rubber expansion joints may not be the most complicated component in a piping system, but it is often misunderstood and misapplied. So I will continue to identify areas of misunderstanding and misapplication throughout this presentation and hope you find it informative. System reliability and efficiency. Owners and maintenance professionals desire piping systems with improved uptime, reliability. Utilizing performance rubber expansion joints, we're going to abbreviate REJs again, can achieve these goals with their rugged construction, high cycle life, and superior chemical and abrasion resistance. Implementing an FMEA, that's Failure Modes and Effects Analysis program, with improved assessment of failure modes, as well as conducting plant surveys performed with traditional and advanced inspection methods, can virtually eliminate unplanned downtime. In addition, this permits a transition to a more desirable replacement for condition-based maintenance program, departing from the previous less desirable calendar-based or run-to-failure practice. Rubber expansion joints, features and benefits, now as a review: absorb large all-directional movement, reduce noise and vibration, have a cycle life in the tens of millions, compensate for misalignment, provide access to piping and equipment, relieve pipe and anchor stresses, have superior chemical and abrasion resistance. Again, not very complicated, but often misapplied and misunderstood. Here the rubber expansion joint moves axially, laterally, angularly, and torsionally, all within a compact body. Degradation and inherent risk. Rubber ages over time and degrades. Stress and temperature accelerate aging. Unchecked degradation can lead to catastrophic failure, but it is also important to recognize that systems designed without rubber expansion joints or other pipe stress considerations lack critical flexibility and can have catastrophic consequences itself. This is another highly misunderstood aspect of rubber expansion joints. What is a performance rubber expansion joint? Now as a review. Utilizing tire cord at a bias ply to optimize directional strength and number of plies. Performance benefits include reduced body thickness and weight, greater movement, lower stiffness or spring rates, larger flange sealing area. Additionally, tire cord is coated with resorcinol formaldehyde latex, RFL, developed by the tire industry to prevent delamination. While this is a review, there are aspects to the performance rubber expansion joint that directly improve efficiency and reliability, and worth re-mentioning in this section. So here we see a clear comparison of a performance design versus a traditional non-performance design. If we look down the performance design column, it's made of EPDM tube as standard, a full 1/4 inch, polyester tire cord reinforced, which is higher tensile and coated with an RFL treatment, has less plies, so it has lower spring rates and greater movements. Utilizes round ASTM C1035 reinforcement, which is high tensile steel, actually close to 3 times that of the lower yield steel A36, and the round shape has less cutting and smoother surface. Wide flowing arch facilitates greater movement, all directional, and lower spring rate. Thinner body facilitates less weight and a larger flange sealing area. High pressure and full vacuum in all sizes. When we compare that to the non-performance design, the chlorobutyl previous standard is used, has less than a 1/4 inch tube. We're going to show in a photo in the next couple slides that it's less than half of the performance joint, and it thins out paper thin at sections. Has a 20-ounce square woven Dacron reinforcement with a lower tensile and no RFL coating. So the increased plies increase the stiffness, spring rate, and decrease the movement capability. Rectangular ASTM A36 reinforcements are used. The tensile is approximately 1/3 that of the high tensile, and the sharp edge is such a problem that some manufacturers have to add additional layers as a sacrificial layer to prevent cutting of the structural plies. This increases the body thickness and decreases performance. The narrow abrupt arch results in less movement and higher spring rates, and the thicker body results in greater weight and a smaller flange sealing area. The smaller flange sealing area you can see from underneath the bolt hole of the non-performance joint is very small, and we have a photo of a rusty leaking flange as a result of this in the upcoming slides. So the non-performance design have higher internal stresses that accelerate the effects of aging. They apply higher stresses to the piping and adjacent equipment by replacing thermal stresses with their own high spring rate. They have limited movement capability with a narrow installation tolerance and other performance limitations, have some maintenance issues with a 5-year typical service life. The performance design have low internal stresses that minimize the effects of aging. They apply lower stress to piping and adjacent equipment by replacing thermal stresses with their own low spring rates, have greater movement capability, allowing for wider installation tolerances without losing performance. Rarely have maintenance issues with a 20+ year service life. Custom performance designs can be built to custom field dimensions, reducing installation time and cost, as well as increasing service life. This maintains 100% performance capability of the rubber expansion joint, and applications include accommodating for large ground settlement or pipe and equipment modification. Of course, we have already talked about different rubber expansion joint styles, including single and multiple arch, reducers, lightweight, high pressure, and high temperature types that all play a part in custom performance replacement expansion joints as well. Traditional and advanced inspection methods can be used to evaluate the condition of rubber expansion joints. These methods include dimensional, visual, physical, and advanced internal. The dimensional inspection will reveal critical information on how hard the expansion joint worked over its life. The information is also used to order a performance replacement rubber expansion joint. Measurements should be taken at all 4 cardinal flange locations and include face-to-face, lateral offset, and torsional offset. Visual inspection methods. External cracking indicates potential internal cracking. Delamination is a consequence of utilizing non-RFL coated fabrics or rubber degradation. Visible blisters directly indicate a compromised tube and fluid wicking through the fabric reinforcement. Ballooning is a sign of compromised fabric. reinforcement, and flange leaking indicates insufficient sealing area and is common in non-performance expansion joints. The bottom right photo is the one I referred to. You see rust and water coming out from the flange, and it's a direct result of the small narrow band of sealing area underneath that bolt that is in the non-performance design. Once rust starts forming on the mating flange, it expands and destroys what little sealing area was there. And some see this as a consequence of an aging expansion joint, but it really should not be. It shouldn't leak for its entire life expectancy. Physical inspections include durometer readings. They reveal critical information on the general rubber expansion joint age and condition. Aged rubber is generally harder and more brittle to the touch, often displaying cracking. ASTM D2240 Short A durometer is recommended for this inspection method. As a lead-in to the advanced internal inspection methods, it is appropriate to mention and reference EPRI's work in this area, including their study on improving the management of rubber expansion joints. EPRI created a technical advisory group with specific goals. Tag contributors included utility sponsors, EPRI representatives, academic researchers, representatives from the rubber expansion joint manufacturers, and inspection vendors. Goals included help the industry better manage the rubber expansion joints to avoid failure, identify common failure modes and environments that are more susceptible to failure and degradation, develop a proactive approach for rubber expansion joints management, inspect rubber expansion joints for degradation prior to failure, identify the primary techniques to inspect for the failure mechanisms of concern. Advanced internal inspection methods. To help put this in perspective, traditional inspection methods provide a sound ability to detect problems related to external degradation and can be an indicator of internal degradation. Significant ambiguity, however, remains in evaluating the actual internal degradation. Removing an expansion joint for internal inspection is costly and may cause unintended damage, and previous volumetric methods for internal inspection have proven unsuccessful because ultrasound attenuates too easily and radiography requires access to both sides of the expansion joint. Microwave scanning standing wave image method have proven to be a sound approach for the internal non-destructive evaluation of rubber expansion joints. So more about microwave scanning standing wave image method. We all recognize a standing wave with its classic sinusoidal shape. Well, a single detector has regions of low intrinsic sensitivity. With a dual detector, areas of low sensitivity on one detector correspond to an area of high sensitivity on the second, ensuring a defect of interest will be detected. A C-channel is calculated and can be used to highlight defects including delamination and significant voids, while minimizing the detection of properties including density and porosity. So we provided this void sample and the non-destructive evaluation volumetric inspection using microwave scanning standing wave image method has shown to be an effective way to detect internal voids. Voids are clearly detected on both the line scan and the 2D scan of this sample. We also provided this delamination and moisture test sample. They were also scanned using the same method. The results successfully detected both the delamination and the presence of moisture within the material. This is significant because both delamination and the presence of internal moisture are common modes of rubber expansion joint failure. They are typically caused by a compromised tube and the fluid wicking through the construction, and were previously undetectable until an advanced stage. Field example of microwave scanning. The inspection probe is moved circumferentially along the part, creating a line scan. Any internal defect will result in a change in voltage and is plotted on the line scan. Any significant change in voltage that cannot be reconciled due to surface geometry is noted for further evaluation. So here is the EPRI's report. We and another manufacturer were recognized for making significant contributions to the development of it. That was published in 2015. So EPRI's report had some limitations or shortcomings, and we put together some supplemental information. The results of the report showed significant promise in the detection of degradation in rubber expansion joints and some potential to detect changes in material properties. A great deal of the report focused on the goal to identify and develop non-destructive evaluation inspection techniques relating to degradation in rubber expansion joints prior to failure. The report was less conclusive relating to the detection of aging effects on rubber expansion joints as well as some of the other TAG goals. We took the initiative to address some of the less conclusive findings by providing supplemental information on industry best practice as presented here, including utilizing performance rubber expansion joints as well as traditional and advanced inspection methods. Additionally, the benefits of an FMEA program which includes a matrix of rubber expansion joint failure modes and corrective actions will be presented next. The report, in combination with this supplemental information, represents a more comprehensive approach to improved rubber expansion joint management and addressing the remaining TAG goals. So as a FMEA review, again, that's failure modes and effects analysis. It's been around since the 1940s. EPRI began looking into using FMEA over a decade ago in their technical report, Streamlined Reliability-Centered Maintenance at Reliant Energy. And EPRI concluded that significant savings will be realized as a result of a decline in performance of breakdown maintenance. Another significant but expected result was the shift in philosophy at Reliant from a reactive to a more proactive approach to maintenance. FMEA program advantages: quantifying a process failure risk by considering its cause, effects, and failure mode, providing a risk priority number based on severity of failure, likelihood of occurrence, and ability to detect, recommending corrective actions and timelines to reduce system risk, and generate new risk priority numbers based on the completion of recommendations. So you can see from this cold to hot chart that a severity of failure, if it was failure is catastrophic and likelihood of occurrence, it's imminent, and ability to detect is undetectable. That's a high risk priority number, and in that situation, additional attention should be taken. Rubber expansion joint FMEA table. This is an example table covering rubber expansion joint processes, including design, installation, operation, and retrofit. Failure modes includes cracking, delamination, blisters, ballooning, and leaking flanges, to name a few. Rubber expansion joint risks are quantified, corrective actions are recommended, and can typically have the original risk priority numbers. The highlighted failure mode is of body blisters and delamination. So when we take a closer look at this failure mode, the process is maintenance, repair, and operation. The failure mode, again, is body blister delamination. Cause is a compromised tube. The effect is likely failure. Severity of failure is high. Likelihood of occurrence is high, and ability to detect was low, so the number is high. This generally produces a high risk priority number. Corrective action included replace with performance rubber expansion joint, which minimizes both the severity of failure and likelihood of occurrence, and utilize traditional advanced inspection methods to improve the ability to detect. Schedule at the next outage, and the severity of failure, likelihood to occur, and the detectability all drops down low to a very low risk priority number. So reliability and efficiency, some conclusions include combining performance rubber expansion joints with traditional and advanced inspection methods can significantly decrease the inherent risk of systems that utilize them. A traditional FMEA program will quantify the reduction in system risk resulting from minimizing the severity of a rubber expansion joint failure and the likelihood of its occurrence, as well as improving the ability to detect rubber expansion joint failures. This permits a transition to a replacement for a condition-based maintenance program, departing from the previous calendar-based or run-to-failure practice. Additionally, and possibly more important, this can virtually eliminate unplanned plant downtime. To round out our presentation, it is appropriate to discuss some manufacturers' qualifications. It is good practice that the manufacturer be ISO 9001, 14001 certified. Manufacturers should be an active member of the Fluid Sealing Association, and the Expansion Joint Piping Technical Handbook is newly revised and filled with industry best practice and performance arrangements. Manufacturers should be an active associate member of the Hydraulic Institute, contributing to important standards and educational material. Experience. Providing all the rubber expansion joints installed in the AP1000 nuclear units at VC Sumner and Plant Vogel, that's 120-inch double arch and 108-inch inline pressure valves shown below, is a good example of experience. Manufacturers should have completed a comprehensive list outlining their experience for reference. Manufacturing capabilities should include standard and custom rubber expansion joints in large diameters and or in offset arrangements. They should also be equipped to accommodate several large-scale projects simultaneously. Testing capabilities should include automated and manual hydro and vacuum testing for all sizes and arrangements. Burst testing and third-party witnessing should also be available. The manufacturer's degreed and licensed engineers should provide unique solutions for even the most demanding applications. Engineering solutions should utilize CAD and advanced simulation software to create optimal solutions. Manufacturers should provide on-site plant surveys and inspections, as well as troubleshooting, training, and expedited replacements when needed. Unique services should be provided, including a best piping practice and optimization program for system optimization with reduced footprint and energy consumption, to minimize loads on piping equipment and support structure, to reduce material and construction cost, for direct engineering support with full comprehension of pipe codes and standards for seamless integration, and to utilize performance rubber expansion joints with advanced restrained and unrestrained designs. Unique services should also include a plant reliability and efficiency program for a transition to a condition-based predictive maintenance program, an FMEA approach with improved assessment of failure modes, for industry best practices, direct training and technical support, and for plant surveys performed with traditional and advanced inspection methods, and to utilize performance replacement rubber expansion joints. Industries and sectors served should include power, both fossil and nuclear, chemical processing, wastewater, mining and mineral processing, pulp and paper processing, steel production, marine, and heating, ventilating, and air conditioning. From the world's largest common cooling water system, Ras Laffan, Qatar, to multiple AP1000 nuclear plants such as at VC Sumner and Vogtle, the manufacturer should collaborate with leading EPC firms and understand the demands of large international new construction projects. Unique services, including best piping practice and optimization programs, is the best way to support this important market segment. The manufacturer should also have installed capacities across multiple industries and sectors dating back decades and experience in developing MRO solutions. Specifically, this should include providing performance replacement expansion joints and educating the customer to ensure the continued efficiency, safety, and reliability of their plants. Unique services, including plant reliability and efficiency program, is the best way to support this important market segment. And manufacturers should be dedicated to providing technical sales and support to original equipment manufacturers across all essential equipment types and around the world. Unique services, including an OEM solutions program, is the best way to support this important market segment. And regarding resources, manufacturers should find it important to not only provide a performance product, but also enrich their clients with detailed application tools and educational materials to help them make the best and most informed decisions. These resources should be easily accessible and include features and benefits, materials of construction, selection and application, catalogs, data sheets, guideline specifications, installation and maintenance instructions, case studies, application demos, solid model images, flange data, technical articles, as well as frequently asked questions, to name a few. And that is the end of our second half of this webinar. If you have any questions, you can email me at the email address shown there. And I'd like to thank you very much.